Hello, welcome back. In this video, I'm going to go through how to calculate the work associated with a polytropic process. So just a reminder, if you haven't watched, watch the YouTube video where I kind of try to describe what a polytropic process is. Remember, this is just a family of curves in a PV diagram that allow us to model just different kinds of machines. So it's not something that you should think of as having maybe physical significance in general. There might be some times where it is, but basically it's just a convenient set of ways to parameterize trajectories. So what we're going to do is calculate the work associated with the polytropic process in going from volume 1 equals 0.1 meters cubed and volume 2, which is 0.2 meters cubed. And I forgot to choose one other thing. The initial pressure, I should have said that, P initial, P1, is 3 atmospheres. Okay, 3 atmospheres. So, I don't know, this could be some sort of a crazy piston cylinder system. Where at state 1, we have V1 equals 0.1 and P1 equals 3 atmospheres. And then the piston will expand out to that dotted lines or something, V2, which is twice as big, so it'd be 0.2 meters cubed. And what we're going to do is consider the cases of N equals 1.5, 1, and 0. Okay, so let's do that. Well, all right, so first let's draw these on a PV diagram. What would these look like? Well, in all cases, we start off at the beginning with, so we have pressure and volume. We start off at 3 atmospheres and some volume. So we'll say this is 0.1 meters cubed, and we'll say that it starts out at 3 ATM. All right, so we start out at state 1, right here. And then before we calculate numbers, it's kind of helpful to have an intuition for this. So to understand that, let's rewrite this polytropic relationship to say P is equal to some constant divided by the volume to the nth power. And then let's consider what happens when N is equal to each of these different numbers. So if N is equal to, actually maybe 1 is an easy one to think about. When N is equal to 1, this is a hyperbolic kind of function. So this would look something like this. So this would be N equals 1. So if that's the case, if you double the volume, I would expect the pressure to drop, and this would be state 2. And it would go from 1 to 2, so we put a little arrow there. What about if, that's for case when N equals 1. If N is equal to 1.5, then it actually would, let me change colors here so it's easy to read this, or easier. That would actually be more steep here and less steep there. So it would look something like that. So this would be N equals 1.5. Right? It's kind of more extreme, but similarly shaped. And then what about N equals 0? When N is equal to 0, this becomes a constant, and you're saying pressure is a constant. So we'll do that one in red. Okay. N equals 0. Now, what I should have done before, I actually made a mistake. The mistake is this green curve. Oh dear, undo that. There you go. Get rid of the green one. The mistake is all I know about the green curve was that it started at this state. Sorry. It doesn't necessarily end. In fact, it won't end at the same place. And you know what? I haven't done the arithmetic beforehand. Let me think for 1 second. It'll be a lower one. So what actually it's going to look like is something more like this. I've exaggerated here, but it'll cross over here. So in the green situation, the second point will be over here, whereas in the red situation, at constant pressure, state 2 would be, I'm sorry, I'm really off my game. The green one, what I know is that the volume is doubled. So all of the final states have to live there. So it'd be something like that. Sorry, there's state 2 on the green curve, and on the red curve, it would be here. So because I know the final volumes are all equal to 0.2 meters cubed, and I have to kind of look at the function here to see that you get different final pressures. So that's kind of interesting. When you change the process, you don't always end up in the same final state. Well, that shouldn't be surprising. I take a good car engine and I dump a bucket of sand in it, change the process, and guess what? It doesn't end up in the same, it doesn't run as well. So the cycle or the process changes the equilibrium states associated with it. So the way you run your machine, which is the same as choosing different values of n, will change the initial and final states. Therefore, it'll change the amount of work associated with each process. Okay, so what we're going to do is evaluate the work in all 3 of these cases and see what we get. Now, to do this, it's handy to do it symbolically. So let's go back to when you don't know what to do, you go back to something that's rock solid, guaranteed to be correct. The definition of boundary work, black. The definition of boundary work is the integral of P dV from state 1 to state 2. That's always true. Then we have to kind of, that's a physics kind of statement. Then we have to mathematize it. We have to turn it into something we can actually perform calculations with. So then we're going to use the fact that I can write pressure as some constant times V to the n, divided by V to the n. So I can plug that into here, and this would tell me that the work equals the integral of the constant over the volume to the nth power dV, and this would be integrated from V1 to V2. All right, well, no problem, right? You just pull this out and pull the constant out. That's some number. And then I have the integral dV over V to the n from V1 to V2. And we just immediately write down the answer. So it's going to be constant times, well, let's see. I add 1 to the exponent and I divide by the new power. So I divide by 1 over, so the exponent here is negative n in the power law. So that's going to be, I add 1 to it, so it's going to be 1 minus n. That's 1 more than negative n. And I have v to the 1 minus n. Easy, nothing easier. Uh-oh. Stop and think for a second. Can you catch a problem or that we might have. Look at the cases we're studying. N equals 1.5, 1, and 0. 1.5, okay, I can plug that in. 0, okay, I can plug that in. What about when n, the index, equals 1? In that case, I have a divided by 0 problem. Well, let's work backwards. What's the origin of that? When n equals 1, this wasn't really a power law kind of integral. It should be a logarithmic integral. So there's a special case. When n equals 1, we get constant times the natural log of v. Oh, I should have been more careful. You have to evaluate that between v1 and v2. Here, it's going to be v2 over v1. Okay, so that's there. So for n not equal to 1, you can use this formula. For n equal to 1, you can use this formula. All right, so that's how you do the calculus part. The rest of it is just arithmetic. So let's go through that. Let's try n equals 1.5. All right, so then my formula says that the work, oh, let me go back. The work is 1 over n, I have to plug in 1.5, so I remember that formula. So, oh dear. All right, so the work would be constant over 1 minus 1.5. And then I would have v raised to the power of 1 minus 1.5. That's negative 0.5. Negative half. All right. Okay, and I have to evaluate that between 0.1 meters cubed and 0.2 meters cubed. Okay, I have to figure out this constant. And I don't know anything about it because it doesn't usually have any physical interpretation that is obvious. So all I can really go back is see where it was first defined. And I remember it was first defined in our formula for the polytropic process. It's that same constant. So P times V to the N is a constant, which means in this case, and that means it's true, which means that the constant can be written as P1 V1 to the N, or it could be equal to P2 V2 to the N, because they're both equal to the constant. That's the whole point of this process. This combination remains constant the whole way. And I just choose whichever one I have more information about. Well, I have more information about state 1. I know the pressure 1 and the volume 1. So I know that P1 is equal to 3 atmospheres. 1 atmosphere is pretty close to 100,000. So this is pretty much 300,000 Pascal. And therefore my constant is going to be P, you know what, there's going to be a better way to write this. So I'm going to hold off on that. Just remember that fact. We will use that. P1, and then, well, okay, we can do it this way. So, all right, so I've got all the things I need. The work is just going to be P1, so that's going to be 3 times 10 to the 5th Pascal times V1, 0.1 meters cubed to the 1.5 divided by negative 0.5. Remember, that's 1 minus 1.5, negative 0.5. It's a pure number, the index. times, and it's going to be 1 over the square root of the final velocity, which is 0.2 meters cubed, minus 1 over the square root of 0.1 meter cubed. And when you go through that, you type it all in, we find that the work will equal, make sure I get this right. I worked this out before, so I just want to write it down here. Yeah, yeah. So I end up with 17,600 joules, which is the same as 17.6 kilojoules. Okay, so you just have to type all that in, and that's what you get. Okay, so all I did was I used the polytropic process to figure out the value for this constant, and that's enough. Let me show one other thing. It's kind of a handy little formula. Because the formula for the work was constant over 1 minus n times, I'll go and evaluate that. I'm going to get v2 to the 1 minus n, sorry, yes, that's right, minus v1 to the 1 minus n from evaluating that integral. I'm just writing out this formula in a little bit more detail. And I can write the constant as either P1 V1 to the n or P2 V2 to the n. I get a choice, and they're equal numerically. So what I can do is distribute this constant inside the parentheses. And on the first term, I'm going to choose to write it using 2's. And on the second term, I'm going to choose to write it using 1's. Numerically, they're the same, but it turns out it's more convenient to do it like that. And when I do that, so that becomes 1 over 1 minus n times P2 V2 to the n, that's coming from the constant, that's my constant, times V2 to the 1 minus n, coming from the integration, minus, now for the second factor, I'll rewrite it using the labels 1, P1, V1 to the n, V1, 1 minus n. And notice what happens. This factor cancels that. This factor cancels this. And I'm left with a more simple expression. Okay, so that's a handy way to write it. If you already know all the pressures and volumes, you can write it that way. So I should have done that earlier, but I'll do it here. All right. All right, let's talk about the second situation. There we had that n equaled 1, in which case we would have pressure equals constant over the volume, which incidentally, that means our constant equals P times V equals P1 V1 or P2 V2 if we knew the final pressures and volume. And the formula for work, well, that was the logarithmic case. So the work is going to be constant times log of V2 over V1, which is going to be, just using one of these, is going to be P1 V1 times the log, and the volume doubled, so it'll be the log of 2. And so I can just plug in the numbers I have. This is like 3 times 10 to the 5 is the pressure in Pascal. The volume was, for volume 1, was 0.1 meter cubed times the log of 2, typing in the numbers and checking with my work from before. I didn't want to do it on the fly. Is 20.79. 20.79 kilopascal or kilojoules, or 20,790 joules. Right, that was n equals 1. And finally, another one, n equals 0. You can either use the formula or the integral is really simple, but I'll just use a formula since we've said that. So in this case, pressure 1 equals pressure 2. It was an isobaric process. In class, we worked out in that one situation, the work is going to equal the pressure times the change in volume. Or we can use the polytropic process formula to say that it was 1 over 1 minus n times the constant. In that case, the constant is the pressure. Sorry, let's do it in stages. Constant times volume 2 minus volume 1. Because if n is 0, that I just get to the first power. And if n is 0, it's 0. And then the constant is supposed to be P times V to the 0 equals constant, which is just the pressure. So I learned that this is 3 atmospheres, so 3 times 10 to the 5 Pascal, approximately, times the change in volume, which is going to be 0.1 meters cubed, which equals 30 kilojoules, or 30,000 joules. So what do we find? N equals, at constant pressure, at n equals 0, we find 30,000 joules, or 30 kilojoules. At n equals 1, we find roughly 20 kilojoules. When n equals 1.5, we found less energy, 17.6 kilojoules. So if we're ranking these, the works we found were as follows. We found the work for n equals 0 greater than the work for n equals 1, greater than the work for n equals 1.5. Go back and think about that. Remember, work is nothing other than the area under these curves. And sure enough, n equals 1.5 has the smallest area, followed by n equals 1, and then the constant pressure curve. So anyway, so hopefully that connects these areas to the work and polytropic processes. All right, thanks for watching. Catch you next time.